Hi everyone. So today, first, we're going to review what we've done last time, which is about the arithmetic gradient series. And then we will talk about geometric gradient series today. And then solve some end of chapter 4 problems. Okay. So last time we've learned about the arithmetic gradient series that describes a uniformly increasing series. And it may be used for the calculation of O&M, which is the operation and maintenance cost in general, and people's salary packages as well, right? So in order to discuss the arithmetic gradient, we use this notation. The capital G represents the fixed amount increment or decrement per each time period. And we also considered a cash flow diagram of uniformly increasing series. So it's something like this. Okay, so in this cash flow, we may say that the first period's cash flow defines the uniform annual series, and the period by period change amount defines the arithmetic gradient series. So if we said A is the uniform annual series, series amount, and the G is the period by period change amount. Okay. Then this uniformly increasing series can be broken into these two parts. The first part for the uniform annual series, so 0, 1, 2, 3, 4, and 5. Plus the arithmetic gradient series, 0, 1, 2, 3, 4, and 5. Like this, okay? Excuse me. So if you look at the arithmetic gradient carefully here, they have cash flow of 0 at the end of period 1, and the first non-zero cash flow occurs at the end of period 2, which means that a three-period arithmetic gradient has only 2 non-zero cash flows. And like this, a 5-period arithmetic gradient has 4 non-zero cash flows, right? Which means that n period arithmetic gradient has n minus 1 non-zero cash flows, right? And which change by amount G, right? Per period. Okay? So this slide summarizes what we've learned last time. So we just talked about factors for an arithmetic gradient G that changed by a constant amount each period. But the real world often has cash flows that have a constant rate of change or uniform rate of change. This type of cash flow is a geometric gradient. Okay? So in order to discuss the geometric gradient series, we use this notation. Small g is the constant growth rate, could be positive or negative per each period, and a sub 1 is the cash flow at period number 1. So let's take a small example for the concept of geometric gradient. So consider an engineer whose starting salary is $30,000 per year with an expected increase of 6% per year for the next 15 years. So the 6% of 30,000 is how much? Is 1,800, right? And an arithmetic gradient of 1,800 leads to a final salary of $55,200. However, a constant 6% increase. So in that case, using the geometric gradient, it leads to a final salary of $67,827. So as you can see here, a geometric gradient is a percentage increase based on the current salary. So it is compounded growth, basically. Is that right? So if you draw a diagram based on these table values, it's going to be, looks like this. So the horizontal axis represents a year, and the vertical axis represents the, let's say, annual salary amount. Okay. So 1, 2, 3, 4 through year 15, right? And basically the geometric series would be something like this. Okay? While the arithmetic series would be something like this. Okay? So this is the, let's say, arithmetic series, and this is the geometric series. Okay? So let's say at 15th year, here we have 67K, and let's say here the diagram is not that accurate, but after 15th year, according to the arithmetic series, it's going to be $55,200, right, based on these two values. And I'd like to let you know that this difference between the arithmetic and geometric gradient is greater for larger rates of change and longer period of time. Okay. Okay. So. And here's the geometric series present worth formula. And just to let you know, for a special case of I equals G, we use this formula 4-30 instead of 4-28. Okay? So let's solve a textbook example problem 4-13. And in this example, we are going to use this geometric gradient present worth formulas. Okay? So the first year maintenance cost for a new car is estimated to be $100. And it increases as a uniform rate of 10% per year. Using an 8% interest rate, calculate the present worth of the cost of the first 5 years of maintenance. Okay. Okay, so we are using 8% of interest rate, and we want to calculate the present worth, PW, of maintenance cost of the first 5 years, where the first 5 years cost is estimated at $100, and it increases at a constant rate of 10% per year, right? So using the formula here, we can get the present worth of P. So here 100 times 1 minus 1 plus G. G is how much? It's a 10%. So it's going to be 0.1, right? And what is the N? N is going to be 5 periods, right? 1 plus 0.08, right? Because we are using 8% interest rate. So 0.08. Now we take the power of negative N, so negative 5, over I minus G. What is I? I is 0.08, and G is 0.1, right? Because here I is 0.08 and G is 0.1, which is not equal to I. So we need to stick to this formula, not this one. Okay? And this value will be $480.42. Okay. So this is the present worth of the cost for the next 5 years of maintenance. Okay. And here's the continuous compounding sinking fund formula and continuous compounding capital recovery formula. Okay. Also, this is the continuous compounding series, compound amount formula, and continuous compounding series present worth formula. So let's take another example, which is 4-15. So in this example, we will be required to use these formulas about the continuous compounding. Okay. So in example 4-1, $500 per year was deposited into a credit union that pays 5% interest compounded annually. At the end of 5 years, $2,763 was in the credit union account. How much would there have been if the institution paid 5% nominal interest compounded continuously? So the $500 were deposited in the credit union, and they pays 5% compounded continuously, right? At the end of each year for 5 years. Then we want to know how much do you have after the fifth deposit. So the formula for the continuous compounding series, compound amount would be F equals A times F given A, and R % over M periods, right? Of course, here A is given as 500, right? And what is value of R? R is 5%, 0.05, and N would be 5 years, right? Or using another formula, which is A times e to the power R times N minus 1 over e to the power R minus 1, right? And using the same value, A equals 500, R is 0.05, N is 5, okay? Then this value should be $2,763.84. And here's the another way. Using the effective interest rate for the continuous compounding, which is I equals e to power R minus 1. So e to power 0.05 minus 1. And this value is 5.1271%. So using this effective interest rate for the continuous compounding, we can get F equals 500 times f given a, 5.1271%, and over 5 periods. And this value is 5.5397. So eventually we're going to have the same value, or it's not exactly the same. There's small differences, but you can get the solution using this way. Okay? Or I believe this is going to be 9. So those two values are exactly the same. Sorry to make you confused. Okay, now let's solve some end of chapter problems from chapter 4. And the very first problem, problem 4-1. So for diagrams A to C, we need to compute the unknown values B, C, and V using the minimum number of compound interest factors. So let's work on the first problem, A. So here we want to determine the present sum P. Let's say P equals C, right? So let me redraw the cash flow diagram. So it's problem number 4-1 and A. So this is the problem, right? And interest rate is 10%. So we want to determine the present sum, which is C, at time period 0. So using the uniform series present worst formula, we may answer this question. So here C is equal to 200 times P given A, and 10% over how many periods? 4 periods, right? So like this. And using the compound interest table from our textbook, we can get this factor value, present, the uniform series present worst factor. So we are looking for 10% interest rate. So you need to look at the page number 613. P given A over 4 periods, which is 3.170. So this is 3.170 times 200. So how much is that? $634. Okay. Okay, then what about question B here? So we want to calculate the future value, future sum V at time period 5. And we can notice that this is not a standard cash flow, right? So, okay. So first, okay, let me think. So here, let's say the future sum V occurs one period earlier. So then we can use the uniform series formula, right? So let me redraw the cash flow diagram here. 0, 1, 2, 3, 4, and 5. %. So if I said, let's say, V sub 4 occurs at the end of period 4, then the uniform series of 10 can be converted to an equivalent future sum of V sub 4. And then this V sub 4 can be converted to an equivalent future value, which is V, original V value, at the end of period 5, right? In that case, the V sub 4 can be considered as a present sum. So here, first, V sub 4 would be 10 times F given A and 10% over 4 period. Once you get the value of V4, you can convert it to the equivalent future sum, which is V. So V would be V4 times F given P, 10% over 1 period. Okay? Of course, this two-step procedure can be combined into a single procedure. So it's going to be V equals V4. V4 is equal to this, right? So 10 times F given A, 10% over 4 period, times F given P, 10% over 1 period, right? And I believe this value would be same as $51.05. Okay? But here, if you read the problem description carefully, it's asking us to find these unknown values using the minimum number of compound interest factors. So we just used how many interest factors? We've used 2 different interest factors, right? So do you have better methodology? which can use smaller number of interest factor than 2. Okay, so here's another way. So this is the original diagram, 3, 4, and 5. I equals 10%, right? And the V is unknown value at the end of period 5, right? So here, if we have one more single payment at the end of period 5. So suppose we have one more single payment of $10 at the end of period 5. Okay? Then what happened? In that case, we may use uniform series compound amount formula. Is that correct? So the V can be computed by 10 times F given A, 10% over how many periods? 5 periods. And then you need to subtract the last payment of $10 at the end of period 5, right? So simply you can subtract by 10 here. Okay? In that way, you can get this future sum of V at the end of period 5. So this is 6.105 minus 10, and which is equal to $51.05. Okay? And because in this case we just use one interest factor, so this would be the answer for this question B, okay, not this one. Even though both methodologies come up with the same answer, simply because the second methodology uses the smaller number of compound interest factor. So I would say this would be the answer. Okay? Okay, so next, part C. So for this case, you may think the given cash flow as a series of 3 single payments, F. Okay? So this given cash flow can be broken into 3 components, like this. Is equal to the first one plus the second one plus the third one. And using the same interest rate, 10%. Okay? And here, let's say, this is P1, say P2, and P3. Then the original present sum of V would be summation of P1, P2, and P3. Right? So how'd you get this value of B? It's going to be 100 times P given F 10% over period 1 plus 100 times P given F 10% over 3 period plus 100 times P given F 10% over 5 period. Okay? This is 5, sorry. This is going to be 100 times 0.9091, 100 times 0.7513 plus 100 times 0.6209. Okay? And the final answer would be $228.13. Okay? Okay, and next problem would be, let's solve problem 4-5. So how much must be deposited now at 5.25% interest to produce $300 at the end of every year for 10 years? So let's draw a cash flow diagram first using the given information. This is the problem number 4-5. So we want to know how much must be deposited right now, right? So we want to know the present sum of P. To produce $300 at the end of every year for the next 10 years, right? So we have A equals $300. Is that right? And the interest rate you're going to use is 5.25%. So how'd you get this present sum of P? It's going to be 300 times P given A and 5.25% over 10 years. And alternatively, you can use this formula, which is A times 1 plus I to the power n minus 1 over I times 1 plus I to the power n, right? So it's going to be 300 times 1 plus 0.0525 to the power 10 minus 1 over 0.0525 and then it's going to be 1.0525, right? To the power 10. Okay? And from my previous calculation, it's going to be $2,289. Okay? So this is the deposited amount right now to produce $300 at the end of every year for the next 10 years. Okay. Then, okay, the next problem would be, okay, let's solve problem 4-7. And just to let you know, these numbers are slightly different from our textbook problem 4-7. That's why I put modification of problem 4-7. Okay. So a car may be purchased with a $3,000 down payment right now, and then 60 monthly payments of $280. If the interest rate is 12% compounded monthly, what is the price of the car? Okay. So for each one of you, you might have very similar situation like this, right? So again, let's draw a cash flow diagram first using this given information. So the down pay amount is $3,000. So P is given as 3,000, right? And 1, 2, 3, 4, up to, let's say 58, 59, and 60. Okay? Well, let me redraw the diagram. So we have down payment of $3,000 because we are going to have negative cash flow. All the arrows should pointing down. Okay, so 0, 1, 2, 3, and so on. 58, 59, up to 60, right? And this monthly payments is equal to 280. Is that right? And it says 12% compounded monthly. So which interest rate we are going to use? We are going to use 1%. Why is that? Because 12% should be divided by 12 because there are 12 months in a year, right? So 1% is the correct interest rate that you are going to use. Okay. So how do you get the car price? $3,000 plus monthly payment of $280. So P given A's, right? And 1% here over next 60 months. So how'd you get this value? We are looking for 1%. P given A over 60 periods, which is 44.955. This is the 44.955. Okay? So it's going to be 15,587. Okay? So this is the answer. This is the price of the car right now. Okay. And next problem is problem number 4-8. Again, let's draw a cash flow diagram. Oh, okay. Let's read the problem description first. A company deposits $2,000 in the bank at the end of every year for 10 years. The company makes no deposits during the subsequent 5 years. If the bank pays 8% interest, how much would be in the account at the end of 15 years? So if we draw the cash flow diagram first, it's going to be like this. So starting from 0, 1, 2, 3, up to, let's say, 9 and 10. So the company deposits $2,000 at the end of every year for the next 10 years, right? So A is going to be 2,000 in this case. And the company makes no deposit during the subsequent 5 years. So 11, 12, 13, 14, and 15. For the next 5 years, company makes no deposit. And if the bank pays 8% interest, how much would be in the account at the end of 15 years? At the end of 15 years. So we want to know this future sum of F at the end of 15 years, right? So, of course, this is not a standard uniform series. So what I'm going to do is set a future value f sub 10 here at the end of period 10. Okay? This is the f sub 10. At the end of period 10. Okay? Then a uniform series of 2,000 can be converted to an equivalent future value, which is f sub 10. Right? After that, this f sub 10 can be converted to an equivalent future value of f at the end of 15. At the end of period 15, right? So of course, in this case, f sub 10 can be considered as a present sum. So first, let's get the value of f sub 10. That's going to be 2,000 times f given a, right? 8% over 10 period. And this value, the factor value, is going to be f given a 14.487 in page number 611. 14.487 times 2,000. And how much is that? So it's going to be $28,974. Okay, and this f sub 10 will be converted to the equivalent future sum, which is f, at the end of period 15. So f would be this value, $28,974 times p. The f given p, 8% over next 5 periods, right? So f given p at 8% over 5 periods is 1.469. This is 1.469. So this is going to be 42,560. Okay. Of course, again, these two steps can be combined into a single procedure. So, which is the same as f equals 2,000 times f given a, 8% over 10 period, times this f given p, 8% over 5 period, right? Which is exactly the same as this. Okay, and next problem that we are going to solve is, what about problem 4-10? A student wants to have $30,000 at graduation 4 years from now.
All right.
Okay, so let me start over. Problem number 4-10. So a student wants to have $30,000 at graduation 4 years from now to buy a new car. His grandfather gave him $10,000 as a high school graduation present. How much must the student save each year if he deposits the $10,000 today and can earn 12% on both the $10,000 and his earnings in a mutual fund his grandfather recommends? Okay, again, let's draw the cash flow diagram first. Okay, so we are working on problem number 4-10. So his grandfather gave him $10,000 right now. And you want to know how much he needs to save each year for the next 4 years, right? So we want to know the value of A for the next 4 years. And then after the 4 years, you want to have $30,000, right? And we are considering the 12% of interest rate. Okay, so these are all the given information. So here, this future sum, $30,000, gonna be same as $10,000 right now. So it's gonna be F given P, 12% over 4 period, plus this annual savings, which is A, F given A, 12% over 4 periods, right? And let's get the factor values. So we are looking for 12%. So you need to look at the page 614, F given P over 4 periods. So this is going to be 1.574. F given A would be 4.779. This is 4.779. Okay. So here we have $10,000 times 1.574 plus 4.779 times A, right? So we want to find the value of A. So how much is that? It's going to be minus, is that right? Okay, so let's get this value. This is going to be $2,984. But I want you to double check this value. Okay. So these are the amount that you need to save for the next 4 years. Okay. Okay. Okay, so I'm going to stop here for today. And next time, we're going to continue to solve the end of chapter 4 problems. Okay? Okay, thank you. Bye-bye.